Good afternoon, how is everybody? Good? My name is Chris Boys. So a little bit about myself. I was very fortunate to be employed by what was British Aircraft Corporation and became British Aerospace. And I had this wonderful opportunity between 1974 and 78 to be sponsored by BAC/British Aerospace to study a degree in Aeronautical Engineering and Design at Loughborough University back in the UK. So I was fortunate that whilst I was doing that study, I spent 6 months at university and 6 months at Filton working on Concorde. And the opportunities were amazing. This was at Filton, and every day I used to go into work and you go through the door and Concorde was there, absolutely beautiful looking airplane. A little bit more from a technical point of view, just see how slender that wing is. Amazing construction, and it was aeroelastic in flight. As a student, I was given full authority to go into all areas of manufacture, assembly, flight test, and access sensitive documents, hopefully to assist me in deciding which department to work in after graduating. And following leaving British Aerospace in '78, I joined a company called Frontier Computer Systems Limited. And for the period 1979 to 1986, I worked on secret air defence systems, which were part of something called UCAG, which is United Kingdom Air Defence Ground Environment, integration of all UK's defence systems. In terms of my flying, whilst I was at university studying and whilst I was working for British Aerospace, I also flew on the University Air Squadron, and the ab initio training there was excellent. Following graduating, I flew privately in UK and France out of Cardiff International Airport and acquired a night VMC and IMC rating. Following that, I came here in '86 and via RACWA acquired a commercial pilot's license, building engine instrument rating and instructor rating, tailwheel, low-level aerobatics. And in 1990 I set up an air charter company, and as chief pilot ran Rapid Air Charter and Tiger Moss Scenic flights to WA. As I was putting these notes together, from memory I started to write a list of technology and operational firsts for Concorde. After several pages, I decided that maybe I needed to abbreviate it for today's presentation. So this is just a bit of an abbreviation of some of those technologies that Concorde embodied. And there were hundreds, maybe thousands. The first supersonic regular public transport aircraft to use fly-by-wire control systems. First supersonic regular public transport to use FADEC, full authority digital engine control systems. First supersonic regular public transport to successfully use variable geometry intakes. And the first supersonic regular public transport to use drag minimization systems. And the last one, first supersonic regular public transport to use turbulence minimization systems. And the last one was very much only possible because of the first one, the fly-by-wire.
That fly-by-wire one, does that include other airliners as well, or just purely and simply the supersonic one?
No, Concorde was the first, and following that, other people have used fly-by-wire, particularly the military, but I believe other commercial aircraft have also. Today I'd like to describe three aspects of Concorde's unique design and the challenges they posed. Firstly, the design of the aircraft flight control system. Secondly, the aircraft's propulsive system. And finally, the design of the aircraft's fuel system. It had many challenges involving airframe cooling, drag minimization, center of gravity control, and fuel conditioning. So in terms of fly-by-wire, some of the benefits of fly-by-wire is that the aircraft construction can be lighter due to eliminating the many needs for mechanical and heavy flight control mechanisms. Use of wires requires less space compared to hydraulic systems. Fly-by-wire, believe it or not, is less complex and more reliable. Additionally, and this is where there was great benefit for Concorde, it's possible to integrate other digital computers into the flight control system to augment aircraft stability, ride quality via turbulence minimization systems. In terms of the control systems, the primary system was fly-by-wire. It was a dual redundant system, and at the time they wanted to make the aircraft as safe as possible, so they had a mechanical backup system. And then if that went wrong, they had a strain gauge signalling system. This is a very simplistic diagram. However, the alternative was a fully integrated diagram for the whole system, which would have been a little bit too hard to explain in the time available. So what we have here is you've got the control yoke, and in roll pitch and via the rudder pedals, there are sensors that sense the movement. And those sensors are then, the output is then converted to an electrical signal. That electrical signal goes back to the power flying control unit and controls the valves where the hydraulics interface to the power flying control unit. Yeah, it's a dual redundant system. The second system, the mechanical signaling system, is exactly what it's described as. You have rods and hydraulic jacks and further rods, and the input occurs at the power flying control unit again. What's the chances of a dual redundant fly-by-wire system failing and a mechanical system failing? So this was a solution. So what they said was if the controls jam, and they're talking about in the cockpit, then strain gauges are attached to the control wheel, roll pitching yaw, or through the rudder pedals yaw. And if you can't move the control, you can partially bend it. And we're only talking about very small amounts. And a strain gauge measures that bending, and the output is then fed back into the fly-by-wire system. So then you've got a further level of redundancy. In terms of Concorde's propulsive system, very unique. Involved variable geometry intakes. The Olympus 593 was a heavily developed turbojet. The Concorde, I believe, is the only commercial airliner that involves any form of thrust augmentation via afterburning. Also, the propulsive system consists of a convergent divergent exhaust ejector system, and the importance of that will become clear shortly. This is a picture which you don't see that often. These are the two intakes here, one side of the aircraft. Now, in this picture, the ramps are fully up. This is a ramp, and this is a ramp. So this one's hinged at the front, and this one's hinged at the back. And this is with the ramp fully down at the front and fully down at the rear. Now, we'll be showing some cross-sections of the whole propulsive unit. Now, if we take a look at the top one, this is a configuration of various ramps and doors. This is the upper ramp, this is the rear ramp. You've got a spill door here, and engine vent bay, primary nozzle, and secondary nozzle. Now, in order to provide a stable airflow into the Olympus engine, the airflow here has got to be subsonic. Yet here, it's Mach 2. So up to takeoff and subsonic flight, what you're interested in is getting a maximum mass flow through. hence these doors are open and the ramps are in the elevated position. When we come to supersonic flight, again we need to have subsonic airflow here. And the way Concorde achieves that is that the upper ramp and this rear ramp are adjusted in an angle to set up these shock waves. And the Mach 2 air, every time it crosses a shock wave, the velocity reduces, the pressure increases, and the temperature of the air increases. So from here, across these shock waves, get back to about Mach 0.6, and the pressure has increased significantly. So this pressure ratio from here to here is 7 to 1, but there's no rotating parts, it's just the doors adjusting. Does anybody want to make a guess what contribution the inlet system makes at Mach 2? If we take a look, you've got the inlet, you've got the Olympus, and you've got the ejector system. So, looking at the inlet, Mach 2, does anybody want to make a guess? What percentage, if it's from here to here is 100%, what percentage do you think the intake creates in terms of thrust? 70 was close, it's 74%. Now if you look at the ejector system, again, does somebody want to guess what proportion of thrust that generates? So you've got 74% here, 18% here. That leaves the engine producing 8% of the thrust at Mach 2. Consequently, that's why you get fantastic range with Concorde. And whilst I was working in flight test, Concorde's the only aircraft I've flown on and witnessed the fuel flows going down after Mach 1.2 as the aircraft goes faster. So in terms of the intakes, it's fully integrated with the Olympus 593 FADEC system, and to compute the position of these doors to optimize the thrust of the overall propulsion system, there are a computer runs and solves 49 complex nonlinear equations, and from memory I believe it was doing that at 100 times a second. It's really important to ensure these ramps are at the correct angle, because if not, if this shock wave breaks down, becomes unattached, then you can get a flow reversal and surge the engine. In most aircraft, it's possible to shut the engine down and continue the flight. There is one issue with Concorde, and that is if you get an engine surge, it's possible for a pressure wave to get behind this door. And these are very lightweight doors, and there's a possibility there of damage. So, looking at the last diagram here, should you have to shut the engine down, what you're trying to do here is minimize the drag of the overall propulsion system. So you drop these ramps down to minimize the airflow in and dump as much as you can out of the inlet. And something strange about Concorde is that if the number one engine fails, the aircraft would normally yaw to the left and roll to the left. But with Concorde, if the number one engine fails, the aircraft actually yaws to the right and rolls to the right, which is a little bit unusual. Okay, just talking a little bit about the Olympus 593. Yes, the engine, as I said, uses a full authority digital engine control system. This leads to optimal performance, enhanced reliability, and longer engine life, because it's possible to control elements to to optimize their operation. For example, in the compressors, you got a low pressure and high pressure compressor sections. On the number 4 engine, below 60 knots, there was a harmonic, and it was potentially going to damage the compressors. So the FADEC was just programmed, so when the pilot demanded full thrust from all engines, number 4 engine, N2, was restricted to 82% until it got to 60 knots, and then it came back up to full power. So there's just an example of the benefits of FADEC.
For any particular reason it was just number 4?
Yes. The vortex that the wing generates operates in different, one's clockwise, one's anti-clockwise. One was compatible with the rotation of the engine components, and the other one was working in opposition. Okay, I mentioned that the inlet has a 7-to-1 compression ratio, even though at a constant Mach number there's no moving parts. But with that 7-to-1 compression ratio, the temperature increases, and that led to a development requirement for the Olympus 593, as it had to use some pretty exotic nickel alloys to cope with the high inlet temperature. Okay, thrust augmentation. The aircraft for takeoff, the afterburners are used. The thrust increase, I think, is about 20%. And the purpose of using afterburner on takeoff was to achieve the field performance with existing runways. And the only other time the afterburner was used, so you took off and started your climb and then shut down the afterburners, and you got to Mach 0.8 and then lit them up again, because the maximum drag's at Mach 1, so you had to punch through this high drag situation. And once you got to Mach 1.2, then you turn them off again, and the aircraft kept accelerating, and as I mentioned earlier, used less fuel in terms of the flow rate. The use of afterburner though on Concorde was a huge challenge, because the aircraft had to operate out of very cold and low elevation airports. It was tested up in Iceland, and it also had to operate out of very high and hot airports like Joburg. And the stability is absolutely essential, because the field performance is based on all 4 engines producing maximum thrust, including afterburner operation. So if you have an instability and you lose an afterburner, so you've only got 3 out of 4, or worse, 2 out of 4, your field performance goes down the, am I allowed to say Danny? Okay. Now in terms of the final part of the propulsion system, this convergent divergent duct, it has 2 purposes. As I mentioned, it creates 18% of the propulsion system thrust at Mach 2, but also in the phase after touchdown, when you're using reverse thrust, those buckets fully open. These inlet doors allow more mass flow through the engine, and therefore maximum retardation. Okay, the next subject is the unique aspects, design requirements of Concorde's fuel system. It's quite a challenge, quite different from subsonic aircraft and aircraft that don't fly above 40,000 feet. At Mach 2 and 60,000 feet, the fuel can vaporize, it can become saturated from an aeration point of view, so that's potentially going to lead to fuel flow problems and thrust from the engines. A second requirement was that as the aircraft accelerates, its centre of pressure gradually moves aft, and at Mach 2 it's moved approximately 2 metres. So to enable stability of the aircraft, the centre of gravity's got to be moved back. So they move about 20 tonnes of fuel to into the main tanks and rear tank from forward tanks to move the centre of gravity. In addition to those two functions, the aircraft structure in the hottest areas is 127 centigrade. Now, well, I think we might all be familiar with fatigue aspects of pressurized aircraft and how many cycles limits the life of the aircraft. Well, with Concorde, you had that. However, it was more extreme because at 60,000 feet, the outside pressure is very much lower than at 40. And then on top of that, you had this frictional heating. And the reason why Concorde was limited to Mach 2.02 maximum, even though it cruised at 2.01, was that it was purely structure related as a limitation due to frictional heating. And so fuel was used and pumped from cold areas of the aircraft into other tanks which were running hotter. So that's how the skin was cooled. And on top of that, then the ancillary systems in the aircraft, like hydraulics, engine oil systems, and excess cabin heat was also transferred to the fuel and effectively dumped overboard.
Chris, the change of the centre of gravity, if you're talking about the centre of pressure migrating 2 metres, that would be in a fairly short time, wouldn't it? So
no, it doesn't happen at once. It's a gradual process, but supersonic, it would move at a higher rate, but the tank transfer pumps were all set to be able to move sufficient fuel, move the centre of gravity. Concorde's got 13 fuel tanks. I know you're going to say I can't count because this one says tank 11, but you'll notice it's 5A and 7A, so that's why it's 13. The fueling tanks 9 and 10 were shifted aft into tank 11 and also into tank 6 and 7.
So I guess you'd move fuel preferentially to tank 11, would you, because the moment arm's longer?
Correct. Yeah, absolutely. The reason why they moved it into these tanks here was that tank 11 wasn't big enough to be able to cope with the required CFG movement. The fuel was shifted aft to move the centre of gravity, and it stayed in the aft position until the commencement of descent and deceleration of the aircraft. So in other words, it's CFG is aft throughout the whole of the cruise phase. This is during climb and acceleration. The reverse happens in descent and deceleration.
is that an automatic function, Chris, or does the flight engineer have to organise this?
This is why the flight engineer was very busy. What happened was the computer systems on board calculated the maximum Mach number for the current CFG position and gave you limits as to how far you could move it forward or aft. And the flight engineer had to flick all these switches and transfer fuel all around to ensure that the CFG was not outside limits. So that they earned their wage. Okay, this comes into the subject of fuel conditioning, which I mentioned is a big challenge on Concorde because of its the low pressure altitude and also the high skin temperature. So the engines had to be fed with fuel from tanks 1, 2, 3 and 4, and now these tanks receive fuel from the remainder of the aircraft aircraft's fuel system, but then they were pressurized to prevent the issue of vaporization and aeration. So all the fuel went through 1, 2, 3 and 4 before getting to the engines. So the fuel system had very many challenges. They had to keep the fuel cold, had to pressurize it, had to keep the airframe cool, had to cool ancillaries. So all this heat it was absorbing had to be dissipated through appropriate tanks. To minimize the drag in flight, the way we trim aircraft that we fly, I'm talking about GA, you use a trim system where you deflect a control system on the tailplane or flying tailplane. What Concorde did was it wanted to have absolute minimum drag from those control surfaces, so it used small amounts of C of G shift to trim the aircraft both longitudinally and laterally, so the elevons were in the optimum position for minimum drag.
So Chris, you're saying that it had no aerodynamic trimming tabs?
Correct. It had no lifting devices, no slats, no flaps. The trim system was via CFG. And I'll just finish off with a short video, but it depicts how Concorde pilots overcame the political attempts to stop Concorde from flying out of JFK. The noise sensors were both upwind and downwind, so the solution was to not fly upwind.
Who was the company that manufactured those engines?
Okay, if you take the propulsive system overall, British Aerospace at Filton produced the inlets. Rolls-Royce at Filton produced the Olympus 593. Ejector reverse thrust assemblies were made by Snecma in France. Bristol originally designed the engine, and then Rolls-Royce took over the development and it became the 593. The 593 is attributed to being produced by Rolls-Royce, even though a huge amount of development was done. I think I've really overused my time. Just to finish off, I'm wearing this Concorde tie which Brian Trubshaw gave to me when we'd been doing some Mach 2 operations, so it was a great time to be involved with the project. Thank you.
I had a variety of flying experiences, and a month up in New Guinea, time in East Malaysia, and more than 25 years with MMA, and sometimes it's a bit hard to know which point is more significant than others, but today it's this, tomorrow it might be something different. I'd like to focus on one very brief but significant event that occurred in my life. And as mentioned, the Concorde came to Perth on 2 occasions that I know of, flying through or whatever. But the particular flight of the Concorde that I'm referring to was in conjunction with a fly over the world with Halley's Comet. So Edmund Halley was Britain's second Astronomer Royal. He lived from 1656 to 1742. At the age of 26, he scientifically and successfully calculated the period of that famous comet, which now carries his name, and he accurately predicted it would return every 76.3 years. Therefore, most people only see it once in their lifetime. In April 1986, again saw this comet in full view to the world, and British Airways planned to fly a comet from London to Auckland with 100 passengers, and to observe the comet over the Indian Ocean, which apparently was the best viewing position, so they would see it on the way over and on the way back. The 100 passengers in the Concorde would take 19 hours to get from London to Auckland. On the way back, I was on the flight that went Perth to Arthur, Port Eden, Newman, back to Perth. And we were getting back into Perth at about 9:30, knowing that the Concorde was coming from Auckland through Perth at about 11 p.m. So I suggested to my co-pilot, Mark Roberts-Thompson, that if we were really smart, stayed at the fence on the edge of the tarmac, when the Concorde came in, we just might get the opportunity to go on board. About half an hour after we leaned up against the wire, another F-28 came in. The boys walked over, seeing us there, recognising who we were. They said, "What are you doing?" And I said, "Well, we're waiting for the Concorde to come back from Auckland. It's due in about an hour's time." "So what are you going to do?" I said, "Well, we'll try and get a look inside." And they said, "Oh, you've got no chance." They went home. We were patient, and perseverance and patience seemed to work pretty well together. It was about 11 p.m. Concorde came in, and because of its size and shape of the tarmac at that time, they parked parallel, and when all the passengers, the cleaning and servicing staff got on board for the catering, etc., the captain came down the step, saw two lonely figures over there wondering what was going on, came over, said hello, we introduced ourselves, and I asked him any chance of having a look on board, and he said, "Yeah, of course." Once the cleaning has been done and the catering has been done, he said, "I'll give you a wave." So when he did, off we went. Going up the stairs, and you know that the Concorde very high off the ground, got into the cabin, and he directed us to the pointy end, as they say. And I was intrigued that the width, you might correct me, only about 2 feet wide, which is 60 centimetres. So some of you fellas are a bit broader in the shoulders than me, but I found that I had to sort of walk carefully. And I think the computer bank was about 3 metres or so long. All these panels on this side, same panels on that side, and then we emerged on the flight deck. So I took up the left seat, Mark took up the right seat, and we sat there. Captain John Cook was his name, gave us a briefing. How much can you learn, how much can you ask in a situation like that, knowing that they're leaving Perth for London fairly soon? Some of the information that he gave us, knowing that the aircraft flies up to 60,000 feet, it equates at Mach 0.2, give or take a few knots, 1,100 knots, 2,100 kilometres an hour, 60,000 feet. That equates, in my calculations, 18.3 nautical miles a minute, or 0.305 nautical miles per second, which is 35 kilometres per minute, or 0.583 kilometres per second. It takes 15 minutes Perth to Kalgoorlie, 10 minutes and 6 seconds to Geraldton, an hour 38 to Sydney, hour 55 to Singapore. Temperatures at the nose rise to 127 degrees Celsius, and on the tail 90 degrees Celsius. So if you're looking for the Concorde, you've got to have long eyesight and do that. At 60,000 feet, and you've heard this from the astronauts, the curvature of the Earth and the darkening of space is easily seen. And from the information I got, the Concorde stretched in length 10 inches and 12 inches in circumference. And then it comes back down to Earth, resumes its almost normal shape and size. Behind the co-pilot's seat, Captain Cook said, "You see this panel, and they're flush. So when we get up into space, at 60,000 feet, he said, you can put your hand between those two panels and it comes back normal again." So how many cycles has the Concorde done? How many times does it expand and shrink? What sort of technology and the design people would be able to tell you that? What if they come up with, how did they find it, and all the complexities that we've seen and heard. The incredible engineering of that aircraft, its performance. I have on reasonably good authority, British Airways never had problems that they couldn't fix or designed to overcome. And it wasn't the BA Concorde that made its fatal landing in flames. But maybe the French didn't want to do anything more with the Concorde because they had the A380 to come along and try and fill the gap, and they would need people to fill that. All too soon our time was up. I think we were only there 10 minutes, about as long as I've been talking to you. What can you learn? What can you see? What can I remember of that time that I sat in the command seat of a Concorde? I asked myself the question, how many Australians would have sat in that seat, in a Concorde, on Australian soil, and how unique was that experience that I've had? All too quickly, it went. Now all too quickly I must went.